Galvanic corrosion occurs when two different metals, such as metal A and metal B, are in electrical contact and face a common environment. A typical instance of galvanic corrosion can be observed when a fastener made of metal A joins two plates composed of another metal, which we can refer to as metal B. In this scenario, both metal A and metal B are exposed to the same environment, with electrical contact between them provided by their physically touching surfaces. This condition is electrically equivalent to connecting a sample of metal A exposed to the environment with a wire to a sample of metal B, which is also facing the same environment. To comprehend the mechanism of galvanic corrosion, however, it is helpful to consider first the behaviors of the surfaces of metals A and B when they are not electrically connected. Let's examine what occurs with metal A and metal B when they corrode independently in the same environment. On the surface of metal A, certain atoms will undergo oxidation, becoming ions that enter the environment. This process is an anodic reaction. Consequently, electrons are liberated within the metal, traveling to a location that supports a cathodic reaction. In this example, we consider the oxygen reduction reaction as the cathodic reaction, which is diffusion limited because the rate of electron consumption on the metal surface is governed by the rate at which oxygen molecules can access the surface. Similarly, on metal B, certain atoms will oxidize, releasing electrons. These will be consumed by the oxygen reduction reaction occurring on the surface of metal B. To maintain charge neutrality, both in the individual metal specimens and the environment, all electrons released by the oxidation of metal A must be consumed by the cathodic reactions taking place on the surface of metal A. Likewise, all electrons produced by the oxidation of metal B must be consumed on the surface of metal B. The important point here is that equilibrium must be established on the surface of each individual metal between the oxidation and reduction reactions, provided the two metals remain disconnected. Thus, the presence of metal B in the same environment as metal A, without any electrical connection between them, does not influence the corrosion rate of metal A, and vice versa. The situation changes when an electrical connection is made between metal A and metal B. Now, if metal A is less noble than metal B, the electrons generated by the oxidation of metal A could be consumed by the cathodic reactions occurring on metal A. However, some of these electrons may also travel to metal B and be consumed by the cathodic reactions on its surface. It might be that, for example, the oxidation of metal A is much easier than that of metal B due to their differing practical nobilities. If the oxidation of metal A occurs much more readily than that of metal B, metal A may generate electrons rapidly enough to consume all the oxygen reaching the surfaces of both metal A and B. We could even encounter a situation where the favorable oxidation of metal A produces sufficient electrons to reduce all the oxygen arriving at both surfaces. In this case, the oxidation of metal B could cease entirely because the electrons produced by its oxidation are no longer required for the cathodic reactions. The electron flow from metal A to metal B is therefore generating a galvanic current flowing from metal B to metal A. This occurs because the direction of current flow, by convention, is always opposite to the movement of electrons. To balance this galvanic current, a corresponding current must flow in the electrolyte from metal A to metal B. So, to encounter a problem of galvanic corrosion, three essential conditions are required. Two different metals must have different oxidation tendencies, or practical nobilities. Additionally, there must be a continuous metal-to-metal electrical contact and also an electrical pathway in the environment to balance the galvanic current between the two metals. If even just one of these three conditions is absent, there is no risk of galvanic corrosion. The primary factor influencing the severity of galvanic corrosion is the difference in practical nobility between the two metals. The concept of practical nobility relates to the free corrosion potential of a material in a specific environment. Different materials exhibit varying corrosion potentials in a particular environment, and generally, when coupling two dissimilar materials, the greater the difference in corrosion potential, the higher the risk of galvanic corrosion. Another critical factor in assessing the risk of galvanic corrosion is the area ratio between the less noble and more noble material, as the cathodic reactions tend to concentrate on the more noble material, while the anodic reactions, which consume the metal, are localized on the less noble material. Thus, if there is galvanic coupling between a small area of less noble material and a large area of more noble material, the anodic current sustained on the less noble material, and so its corrosion, will be greatly increased due to the substantial area provided by the more noble material to support the cathodic reaction. Conversely, if the area of less noble material is significantly larger than that of the more noble material, the effects of galvanic corrosion are less severe because the impact of the cathodic current generated on the more noble material is distributed over a wider area of the less noble material. In practical terms, there is a higher risk of galvanic corrosion when, for example, a less noble material fastener is coupled to a more noble material plate, compared to a scenario where a fastener of the more noble material is connected to a plate of the less noble material. This has been a brief overview of galvanic corrosion. For a more in-depth discussion of corrosion mechanisms and processes, have a look at the many corrosion courses available on Corrozone, where we discuss this and many other topics in much more detail.